Hi, I'm Brandon. Welcome to the Molecular Foundry. We're part of Berkeley Lab here, and we're funded by the Department of Energy as a user facility in nanoscience. Now, the Molecular Foundry serves users from all around the world, like Ambika Bum, who is an industrial user. She works at Bikanta, and she is working on nanodiamonds in 3 of our 7 facilities here.
Hi, Brandon. So it's exciting to be able to tell you what we're doing here at the Molecular Foundry. At Bikanta, we are using nanodiamonds, these tiny little bits of diamond dust, to redefine what can be done with medical imaging, and particularly with optical imaging. So the reason for all of this work is, if you think about in the big picture about cancer detection, today 44% of the population develops some form of cancer. So if you're right now at your desk, sitting next to someone, and you turn and look at them, it's unfortunately likely that between you and that person, someone will have some form of cancer. The good news is we've gotten better at treating it, but we need to get even better at finding it earlier, because it helps in the prognosis of the patient, it helps in healthcare costs, and in every aspect of the treatment. So that's where it becomes with the kinds of agents that are out there, either with signal loss problems or toxicity concerns. And that's where we're developing nanodiamonds that resolve those issues and can allow you to image deeper into tissue and very sensitively. So the way to think about diamonds is that they are tiny little flashlights that we can use to shine light onto different kinds of problems to help us detect disease. So what we do is we inject the diamonds into the patient. We have ways to target them to stick to tumor. They give off a signal, and then we find that signal to better detect the tumor and then make our diagnosis and the treatment plans that are needed to treat the patient. So what we do here at the Molecular Foundry is that we develop that technology, and I'm going to take you through with the rest of our team at Bikanta of how we use this facility and the government's resources to help us really make sure we're making the best kinds of products. And we're starting here on the inorganic floor, where we do the synthesis and show a little bit of how we characterize things. We're going to go down then to the first floor, where we'll look at electron microscopy and how we do further characterization, and then come up to the 5th floor, which is the biological nanostructures floor, and show you how we actually do imaging with them. So you get the idea that this kind of science is very interdisciplinary. You can't do it in a bubble in one specific kind of field. You have to bring in the resources of different kinds of areas. So let's start by first going into one of the chemistry synthesis labs here. So that was a bunch of glove boxes. Take you through.
This particle will be selectively attached to the cancer surface, cancer cell surface, provide early fluorescent detection for cancer cells. So let me show you some of our sample testing in Palestine. We are running the particle size, try to measure the particle size after certain modification. This is dynamic light scattering, we also call DLS. It measures the Brownian motion of particle in the solution, here actually in the water. So every time we do the coating, we try to measure the particle size to try to figure out how thick the coating is, and how this coating provides the stability, again, the biostability, biocompatibility. So we did a lot of them. We not only tested the coating on the DI water, also in some PBS solution. That's exactly same composition in the bloodstream, like same salt, same pH condition. And this is normally what we did the daily job. And we also measure the coating, how much coating on the surface, how that coating, the weight against the particle size. And also occasionally we measure the chemical structure of the coating conducted by the FTIR spectrum.
So let's head out to another floor and show you some more characterization. There was the development of the particle, the coatings, and looking at them in solution. And that's more of a bulk measurement. But at times we want to look at them as individual particles to understand their aggregation and whatnot. So now we're going to head down to electron microscopy and show you how we do that.
So the Foundry has 7 facilities, and we just saw one of the facilities where we make really, really small things. We're going down to the first floor to look at these small things. Since nanomaterials and nanodiamonds specifically are smaller than light itself, we need to use tools that are really special and really unique to this facility in order to look at them. So what we're going to use is something called an electron microscope. Electron microscopes are much like optical microscopes, except instead of using light that bounce off materials, they use electrons. Electrons, being smaller than atoms, are able to see things that are nanoscale, if not even atomic in scale.
So this is Min. She's another scientist on our team, and she's going to tell you about how to use electron microscopy.
Hi, so we are interested to look at what the nanodiamonds actually look like. So I think everybody knows what a diamond looks like. So to see a nanodiamond, we have to use an electron microscope. So this is an image of nanodiamonds that has been magnifying 20,000 times. As you can see, they come in all different sizes and shapes. So let's take a closer look at that guy by zooming it in. Let's zoom it in, maybe. So as you can see, this diamond, they don't look anything like the diamonds that we are familiar with. This is because they have been crushed into very, very small particles. So using the electron microscope, we can then perform analysis of our sample, because we are coating the sample to prevent aggregation. As you can see in this picture right here, this is a surface coating that has gone bad, that we have particles that has a large aggregates. That's something that we don't want. So ideally, when we coat nanodiamonds, we want them to be remain as individual particles. So that's something that we are working towards at the Foundry. And
yeah, so these properties are important because when you inject an aggregate of materials into the bloodstream, they go to different parts of the body. They'll get sent to the liver very quickly, and they'll just not circulate in blood for a long time. Whereas if you have individually coated single diamonds, they act, it's called monodispersity, they act significantly better at reaching the targets that we want to because they stay in the bloodstream longer. And so we've worked on a number of different coating strategies that allow that monodispersity. And all of this work, it's really important to be able to see what you're doing, to characterize it all. As a startup, you have limited financial resources, and it's not necessarily the wisest decision to purchase every single one of these instruments. So having a facility like this to access is fantastic.
So we're going up to the 5th floor here, and so we went from the inorganic facility.
Uh-oh.
There goes the elevator. So we went from the inorganic facility, which made these nanodiamonds, down to the imaging facility, where we are looking at the diamonds to look at the diamonds in a different way. The Foundry, as I said, is a user facility, and it allows people like Ambika to take advantage of all of these different pieces of equipment all under one roof. And they're allowed to do so free of charge because we are funded by the federal government. The idea is that no matter where in the world a good idea comes from, that the Foundry is there to help facilitate those ideas, either through the use of equipment or through the expertise of our great staff.
So, thus far we have talked about the synthesis and now some characterization. But the next thing we want to show you is some actual application. How do we image these diamonds? So in this room, this is the microscopy room on the 5th floor, where we get to use these fancy microscopes here. There's total internal reflection fluorescence microscopy as well as confocal. I'm going to show you first some images on confocal imaging. So how we image these diamonds is we shoot one color at them, they absorb that color and then give back another color. So we shoot a green laser at it and it emits a red color. So to demonstrate that, if you look in closely over here, what we have is a sample of essentially very common rubber that we've embedded with different nanodiamond particles, and we're exciting it with one color laser, and it's emitting red light, a near infrared color, which you can't necessarily see with your naked eye, but here you can see we're imaging nanodiamonds in that 3D structure. And what we can do is create a Z-stack, or a layer by layer stack of the diamonds throughout this phantom that we've created. And it's very sensitive, so you can see individual particles. This is the same kind of concept of thing we would do in tissue. So this demonstrates in principle how we would image diamonds throughout tissue. And where we're trying to take this in a clinical direction is for imaging targets in skin, for instance, when you're trying to image where melanoma is or where basal cell carcinoma is. So this is one property of the diamonds, the fluorescence, but they also have a second property, which is that they are sensitive to magnetic fields. And Roger is going to talk a little bit more about how we actually translate this into a clinical application.
Hello, my name is Roger York and I'm an instrumentation engineer at Bikanta. So as was mentioned previously, we can take our nanodiamonds and coat the surfaces of them with selective targeting molecules, for example antibodies or biotin, that allow us to target some particular type of cell, for example a tumor or some other tissue that we're interested in. If we exploit these properties of our nanoparticles, we get some very interesting results. In this particular experiment, we have a mouse that we imaged, and you see two images here, one using conventional technology and one using our platform technology. In these images, we've exploited the fact that our nanoparticle has two particular properties that are useful, namely the fluorescence properties and the fact that they can be magnetically modulated. This allows us to see at a low concentration of nanoparticles a lymph node, which is important for staging cancer.
So these are this is one example of a cancer detection method we would do, where if you had a tumor, you're trying to see how much it's spread, you want to see if it's gone into the lymphatic node. You need to have a good imaging agent that highlights it, and that's the kind of work that we are doing here at Bikanta. And you can see how powerful the same mouse in conventional technology versus in ours, how powerful that imaging method can be. So we're very excited about the work that we're doing here, and the Molecular Foundry really enables us to be able to do that. The amount of R&D we've accomplished in just a short amount of time, the different kinds of resources, the different staff that we have here to access, it's really unique to a user facility like this, and not every startup is lucky enough to have access to such resources. So we're very grateful for what we get to do here, so that we can work towards our big picture goals in cancer detection. So thanks.
We've got a question.
All right.
What are your backgrounds that got you into this interesting technology and science?
Sure. So my background is in nanomedicine. I did biomedical engineering as undergrad, went on to do a PhD in this space and focus on really nanotechnology for imaging and drug delivery. The different people we just walked through, Min and Lee, are also very similar, have chemistry backgrounds, nanoparticle development, and Roger's background is widespreading, but primarily what he's helping the team with here is in optics engineering. So everyone has significant experience academically in different kinds of areas, but we're trying to use all those skills for this particular technology that we're trying to move forward. Bye. Have a good day, everyone.